So we already discussed about harmonic oscillator. And we found that the vibrational energy E nu is equal to nu plus 1 by half of h cut omega oscillations. And for ground state, that is 0 point energy, that is E naught. This is yes, it is nu equal to 0. It is 1 by 2 omega oscillations, and this is, sorry, h except h. When I'm writing this nu, it is wave number actually in centimeter inverse. So this is centimeter inverse. Okay. With the selection rule, delta nu plus minus 1, and the energy levels are equally spaced. This, if you have E here, so you have, this is 1 by 2 omega oscillation, this is 3 by 2 omega oscillation, 5 by 2 omega oscillation, and this is nu equal to 1, 2, 3, 4, like this. This is R, internuclear distance. Okay, so they are all required. Now, this was a harmonic oscillator where we assumed that the bond between these two changes such that there's a vibration, but it is harmonic vibration. Now, what happens when there are anharmonic terms? Because real molecules actually, they do not actually obey exactly the laws of simple harmonic motion. But we should remember that the bonds, chemical bonds, they are elastic, and bonds are elastic, but there is a difference between the real bonds and the simple harmonic motion in other cases like Hooke's law. But these bonds are elastic, but they are not so homogeneous. Not so homogeneous. Such that to obey Hooke's law, so that they will obey Hooke's law. But they do, that means they do not obey Hooke's law completely, as practically it has been found. That means if we can give some energy to the molecule, and this bond will stretch, this bond, it will stretch, maybe in or out, relax, or it may stretch in, or it may be pulled apart, and a point will come while it can break. At some particular instant of point or time, when you give more energy, the bond can break. So that means the molecule, it is dissociated. Dissociated means broken down into individual atoms. So it dissociates into atoms. So that means when the energy is large, when the vibrations are such that the bonds are broken down, and when bonds broke down, the molecule is dissociated into individual atoms. So what happens then? How to this analyze the vibrational spectra at that time? So that means the amplitude of vibration is large. The amplitude of vibration is large. Okay. And in this case, the bonds are broken down when you have the amplitudes For example, we can say that there is not an exact point, but and roughly you can say that when you stretch a chemical bond, when you stretch, that means when the chemical bonds are stretched apart greater than 10% of the bond length. So that means if there's a 10 angstrom bond and you stretch it by 1 angstrom, this is 10%. Okay, when you stretch it by more than this 1 angstrom, that is more than the 10%, that means it was initially at equilibrium distance is 10 angstrom, you stretched it up to 12 angstrom, that means 2 angstrom you had, which is more than the 10%, then you can say that the bond can break down. The bond is an anharmonic regime. So when this happens, the harmonic oscillator, that curve, the energy internuclear distance ER curve, which was actually like this, it goes now like this. This is E here. This is the R internuclear distance or equilibrium. Here is R equilibrium. This is R equilibrium. This is R internuclear distance. And this is the energy where a molecule breaks down into atoms here. This. Okay. Up to here it was okay, but here if you see that it has broken down apart. Now the energy, whatever when you are increase this, the atoms are separated from each other, it becomes independent of the incident energy. There is no effect on the vibration spectra because it is now, the atoms are now broken apart, they are very far apart from each other. They don't, the individual vibration has no effect on the another one. And this is called as here the energy, this energy at which the atoms break, this molecule breaks apart, it is called as dissociation energy. And this is the here D equilibrium, dissociation energy at, this is at equilibrium, and here it goes away. This is D equilibrium. Okay, dissociation energy. So people try to find out the reason and they try to find out the expression for this type of spectra, this molecular spectra, and it is an empirical expression. So there it has not been derived from somewhere, it has been just the terms are brought and they have been combined to form an equation. Okay, and there's an approximation which was derived by actually PM Morse. And he said that this curve, this behavior, this here, this is actually a particular type of function which is called as Morse function. This curve, this whole curve actually, this. So this is a Morse function actually, this curve behaves as a Morse function, and this is an equilibrium which we already discussed. This parabola, this is, sorry, this is a parabola, this. Yeah. Okay, and the function, the approximation for an anharmonic vibrations of a molecule is exactly approximated by the Morse function. And what Morse function actually is, so it is E is equal to D equilibrium, that is the dissociation energy constant, minus 1 exponential of A or equilibrium minus R whole square. And this A is actually a constant for a given molecule. Particular molecule. Okay, or equilibrium, this is the equilibrium distance, R is up to which you stretch it, the distance, total distance, this is the equilibrium distance. This d is the distortion energy, actually d equilibrium at equilibrium. And when we use this E in Schrodinger equation, because you find the energy eigenvalues from the Schrodinger equation. So instead of simple E equal to nu plus 1 by 2 omega h cut omega, that eigenvalue which you obtain, you find EV for an n-harmonic oscillator is, this is for the case of this, what is called as harmonic oscillation part, minus some part of energy to be given to the n-harmonic. But this is in centimeter inverse, remember that. And nu is again equal to 0, 1, 2. Here I have used two terms, different terms. One is omega E and XE. This is the oscillation frequency. This is the oscillation frequency. And this is in wave numbers in centimeter inverse. This XE is n-harmonicity constant. N-harmonicity constant. And it is always for, if there is a stretching, it is positive. So XE is greater than 0 for stretching. When we stretch a bond due to n-harmonicity, and is small. Small XE, that is XE is approximately equal to plus 0.01. This very small value. That means these vibration levels where there is a n-harmonicity, these vibration levels are actually, their spacing is determined by this n-harmonicity constant. Since it is very small, so these vibration levels will be crowded. They will be closely spaced. And if you can rearrange this expression, we can rearrange this expression for n-harmonic vibrations. He knew what I will do. I will take this common, this term, and let us write first it. I can write it. Take omega E common. I will write I have taken this and this common, nu plus 1 by 2. Yeah, here it is square, here it is 1, so I have taken this common here and omega here. So here it remains 1 minus nu plus 1 by 2. Okay, and there is XE. Here XE is here. N-harmonicity constant will be there. Okay. So this is an approximation. And if we want to express it more precisely, then when a molecule vibrates at higher frequencies, we have to consider higher order vibrations. And when we take higher order, that means for higher energy levels, they require cubic, quadratic terms, quadratic. Okay, this is a quadratic actually. This is quadratic, and then we will need cubic, quadratic, fifth power of the nu plus 1 by 2. With n-harmonicity constants different. Like for quadratic, we have taken the n-harmonicity constant XE. So for cubic, we will take it different because it will be, it will change with the amplitude actually. Okay, and YE, then ZE, and but it diminishes the magnitude of those vibrations at higher order, higher magnitudes, higher order vibrations. They will diminish actually because the amplitude. It is just like you approximate. According to that binomial theorem, you have seen that this expansion according to binomial theorem, or then Taylor series expansion. So here we are taking up to the only the second order terms when the amplitude increases, and we see that then the energy levels, if you plot in this case, it's not so accurate. I will try to redraw it. Yeah, somehow it is better. Same, but there is an, these are the harmonics. Remember that this is the harmonic case. Then you go into an harmonic here. These are closely spaced from here. Okay. Here we don't need actually because they are separated apart. Here when you draw this, sorry, it will go now straight. This is D equilibrium. Then here this, from this ground state to this, it is D naught. This is the dissociation energy for the 0 point energy, this here D naught for nu equal to 0. And when you calculate the transitions, the transitions will go here. There is now no restriction on delta nu. It is plus minus 1, plus minus 2, plus minus 3, because amplitude is very large, energy ranges are very large. So when energy ranges are large, the transition can occur from lower level to the higher levels, one after another, up to second level, up to third, because it depends upon how much energy you are giving. Okay, and then delta nu is equal to plus minus 1, plus minus 2, plus minus 3. Remember that this is an important difference. Okay, and if you compare mathematically, if we take the mathematical expression like this, I have written in above this. So let me do it. You remember that E nu for harmonic oscillator, that is nu plus 1 by 2 omega oscillation. This is the previous case for harmonic vibrations. This is a harmonic vibrator for harmonic vibrations. Compare this equation with this. Compare these two. So I can write nu is equal to, if you take this, this is here, then I can find out omega oscillation equal to this part, whole this part. This. And the n harmony, what this expression gives us, this expression results in the statement that the n harmonic oscillator behaves like a harmonic oscillator. It will behave like a harmonic oscillator when the oscillation frequency it decreases with increasing nu here. So that means it is harmonic oscillator, but the oscillation frequency in this case is decreasing steadily, that means constantly, with increasing nu. Now suppose that we put nu equal to minus 1 by 2. let us suppose that we put nu equal to minus 1 by 2 here. What will happen? This is called, this will give us actually a physical result actually. It is called as equilibrium oscillation frequency of the n-harmonic oscillator, n-harmonic system, but it is hypothetical. Remember that. For any real state, if there's a real state, the oscillatory frequency is given by this n-harmonic oscillator in case of n-harmonic system. And this states that this is the frequency, equilibrium oscillation frequency for an n-harmonic system. That means when the system is in n-harmonic motion, but this frequency is for infinitely small vibrations about equilibrium point. So it is the equilibrium oscillation frequency in the case of an n-harmonic system, but it is for infinitely small vibrations about the equilibrium position. Because this point, this goes to 0, and it is omega E1. Okay, very small. It is minus 1 by 2. So you are decreasing actually, nu, negative nu. That is why it's called hypothetical. But it gives us a magnitude of an infinitely small vibration. This is the minimum vibration we can have. Because if you put 0 there, you still have an harmonic term there. You cannot find the minimum energy from the 0. So for getting the minimum energy, we put it minus 1 by 2. So for now, take the different states now. For nu equal to 0, omega naught will be equal to from this. Omega oscillation becomes omega naught here, this expression. Here. Nu equal to 0, so it is 1 minus 1 by 2 xc. It is in centimeter inverse. And if you find E naught is energy, it is 1 by 2 this you will find from this expression here. And if you see here, there's a difference between of harmonic and anharmonic vibrator. E naught was simply 1 by 2 nu omega E. And here it is 1 by 2 omega E 1 minus x, 1 by 2 xe. So there is an anharmonic constant, anharmonic coefficient in this. And selection rule I have already given you. Now, let us see the difference. When there is a transition nu equal to 0 to nu equal to 1, delta nu is plus 1. Now there is no restriction on delta nu. It is plus minus 1, plus minus 2, plus minus 3, emission and absorption both. So when the intensity is very large for this in transition, so delta E will be equal to nu equal to 1 minus E nu equal to 0. Delta E is equal to, you are saying that it is the 1 plus 1 by 2 omega e minus xe into 1 plus 1 by 2 whole square omega e minus then 1 by 2 omega e minus 1 by 2 xe omega e. You mean to, let's say, like this.
सर E1 निकला है हमें 3/2 ओमेगा E into 1 minus 3/2 XC और
Yes.
E0 निकला है 1/2 ओमेगा E into 1 minus 1/2 XC. सर इसी को अगर हम करता है तो सीधे ही निकलेगा.
Yeah, this is it is okay. So this is 3/2 omega e minus
1 minus 3/2 XC.
This is 1
into
minus
1
3,
minus
this whole term.
into 1.
Yeah,
Yes,
this
sir.
is the xe. It is 3/2. This is square actually. That's why it is minus
Yes.
1/2 omega e minus 1 by 4 xe omega e.
सर
So
ये लास्ट वाली प्लस आएगी. Plus
yeah,
1 by
plus,
4.
yeah, this is plus because there is minus. Yes. So this is
Yes,
3/2 omega e minus this is 9 by 4 xe omega e plus 1 by 4 xe omega e. Okay. Then this is 3/2 omega e. There is minus 1 by 2 omega e. Now it's okay. It is 3/2 minus 1 by 2. It is omega e minus 9 by 4 minus 1 by 4 xe omega e. So this is equal to 1 by 2. 1. This is 1. So this is omega e
omega E
minus
yes, sir.
This is 8 by 4. That is 2.
2. Yes, sir.
That is equal to omega e into 1 minus 2 xe. This is the actually delta e nu equal to 0 to 1. Similarly, if you find nu equal to 0 to nu equal to 2, because we can go up to plus minus 2 now. So then we find that is delta nu is equal to plus 2. And similarly, if you use this same expression, you will find that delta e is equal to 2 omega e into 1 minus 3 xe. This is in centimeter inverse. And similarly, I have, if you take this, wait, if you take nu equal to 0 to nu equal to 3, because we have delta nu equal to plus minus 3, so we can go up to plus 3, and when you put up the values nu equal to 0 and then nu equal to 3, then subtract nu equal to 0 from nu equal to 3, you will find delta e is equal to 3 omega e 1 minus 4 xe. And you see that there is a pattern actually in this case. And in the first case, you have seen it is omega e into 1 minus 2 xe. Then in the second case, it is 2 omega e into 1 minus 3 xe. Then in third, it is 3 omega e into 1 minus 4 xe. So there is an increase every time, but these corresponds to a band of absorption liners for nu equal to 0 to higher energy levels, from nu equal to 0. And to the approximation, if we use xe equal to 0.001, if we use n-harmonicity constant is 0.001, you will find that these spectral lines, because that means we almost ignore it because it is 0.001, so that means approximately equal to 0, this term. Then what you will find, so delta e is equal to, first it is omega e, second is 2 omega e, third is 3 omega e, in the next one it will be 4 omega e. So these are the multiples of omega e. And this line omega e, which corresponds from 0 to 1, it has a maximum probability, and it is called as the fundamental absorption. It is called as fundamental absorption. This is called as first overtone. This is called as second overtone. This is third overtone. So that is how we characterize the absorption spectra of an anharmonic vibrating diatomic molecule. This is for approximation. We have used the approximation. The anharmonicity constant is very small. That means we are not giving so much of magnitude to the anharmonicity. That means the bonds will break totally. We are going up to higher magnitudes, but only it remains anharmonic. That means the amplitude is not the harmonic. It's not the linear function of displacement. It is now the quadratic function of that R minus RE. R minus R equilibrium. Okay. So that is how we deal with this anharmonic vibrator. So in a nutshell, I can say that we take a dissociation constant, dissociation energy, then we use the quadratic terms like we did it in non-rigid rotor, like in the case of non-rigid rotor. So here we did it for the non-anharmonic vibrator. Okay, and there was then the E is equal to 1. There is nu plus 1 by 2 omega E. This is in the wave numbers. When I take E, this E, when I take this E, it is a total energy. Then there is H cut here, H cut omega. Okay, and this is energy. That is the wave number here. So nu plus, there is minus, then the quadratic term corresponding to anharmonicity. This is in centimeter inverse. Okay, and then accordingly we calculate the energy spacings between the energy levels and the various values of the absorption bands, and we find that when we use some particular approximation like nu equal to minus 1 by 2, and we find that omega oscillation becomes omega equilibrium. This is a hypothetical minimum energy value in case of anharmonic oscillator, anharmonic vibrations. Okay, this is the equilibrium oscillation frequency for minimum energy. That is why it's called equilibrium, because it is a minimum energy. And the selection rule for this is delta nu equal to plus minus 1 plus minus 2 plus minus 3 to higher order. Then you can calculate the energy levels. That is delta E equal to 0 to E equal to 1, and delta E, this is 1. Similarly, you can calculate from 2 to 3 or 2 to back to 1, because this is plus minus 1. So you can go in the emission as well as in the absorption. When plus 1, it is absorption. When it's minus 1, it is emission. Okay. And I think this completes the vibrational spectra. Then there is a vibrational rotational spectra. That is diatomic vibrating rotator. That means we take vibrationals as well as rotationals combinedly, which is most practical case.